Hey everyone, and welcome to today's explainer. I am absolutely thrilled to guide you through this because today we are going to master the absolute magic of carbon. If you're a 10th standard student tackling your science curriculum, you are exactly in the right place. We're going to build complete conceptual mastery of Chapter 4 right from the ground up. Carbon is, without a doubt, the ultimate, most versatile Lego brick of the entire universe. So grab your notebooks, get comfortable, and let's decode the foundation of organic chemistry together.
Okay, so let's start with a really crazy paradox. Think about these numbers for a second. The Earth's crust has a meager, tiny 0.02% carbon in the form of minerals, like coal and petroleum. In the atmosphere, just 0.03% carbon dioxide. But despite being incredibly rare, carbon forms the basis of all our food, clothes, medicines, books, and literally every single living structure on this planet. How is that even possible? How does such a rare element completely dominate the chemistry of life?
Well, here is our game plan for today to figure that out. We're covering 1. The carbon dilemma, 2. Covalent bonds and sharing, 3. The superpowers, chains and rings, 4. The homologous series, and finally 5. Reactions and the real world. Let's jump right in.
Starting with Section 1, the carbon dilemma. So what exactly is the atomic problem that carbon is facing? Well, if you recall your electron configurations, carbon has an atomic number of 6. That means it has 2 electrons in its inner shell and 4 valence electrons in its outermost shell. Now, like all elements, it desperately wants a completely filled outer shell to achieve that super stable, noble gas configuration. It wants 8. So what on earth does it do with those 4 valence electrons?
Picture this, like a massive chemical tug-of-war. Option 1. Carbon tries to gain 4 electrons to form a C4- anion. But its tiny nucleus only has 6 protons. It would be incredibly difficult for 6 protons to hold on to 10 total electrons. It just wouldn't work. Okay, so option 2. It loses 4 electrons to form a C4+ cation. But ripping away 4 whole electrons requires a massive amount of energy, and it would leave behind a nucleus struggling to hold just 2 electrons. So carbon is totally stuck. It can't steal, and it can't give away.
Moving on to Section 2, covalent bonds and sharing. So, what's the brilliant solution to this energetic dilemma? Instead of giving or taking, it shares.
Take a look at how this sharing works with ethane, C2H6. Notice how the 2 carbon atoms link together with a single bond, and then perfectly share pairs of electrons with hydrogen atoms to satisfy all their remaining valencies. Because they're sharing electron pairs, they form what we call single covalent bonds. Now, these covalently bonded molecules have really strong bonds inside the molecule itself, but the intermolecular forces between different molecules are weak, and that is exactly why carbon compounds usually have quite low melting and boiling points, and why they're poor conductors of electricity. Compounds linked by only single bonds are called saturated compounds. They are relatively relaxed, full, and stable.
But what if there just aren't enough hydrogen atoms to go around? Well, carbon adapts. Check out ethene, C2H4. Step 1, the carbons link up. Step 2, we add the hydrogens. But wait, 1 valency per carbon is still empty, so carbon just forms a double bond with the other carbon atom to satisfy the requirements. Whenever we have double or triple bonds between carbon atoms, we call them unsaturated carbon compounds. And because of these double or triple bonds, they are way more reactive than their saturated single bond cousins.
Which brings us to Section 3, the superpowers, chains and rings. Okay, so carbon shares electrons. Great, but why does carbon form literally millions of organic compounds while other sharing elements don't? It all comes down to 2 absolute superpowers.
Superpower number 1 is catenation. Imagine carbon atoms holding hands to form a massive human chain. No other element exhibits this property to the extent seen in carbon. Now you might be thinking, hey, doesn't silicon do this? And yeah, actually, silicon does form chains with hydrogen, up to maybe 7 or 8 atoms long, but those are highly reactive and very unstable. Because the carbon atom is so incredibly small, its nucleus holds on super tightly to those shared electron pairs. The carbon-carbon bond is exceptionally strong and stable, allowing for incredibly long chains.
Superpower number 2 is tetravalency. Since it has a valency of 4, every single carbon atom is basically a 4-way intersection. It can bond with 4 other atoms of carbon, or it can branch out and bond with oxygen, hydrogen, nitrogen, sulfur, or chlorine. This allows for just an endless, dizzying array of chemical combinations with highly specific properties depending entirely on what element joins the intersection. Let's do a quick recap on a golden rule here. When carbon uses these superpowers to build hydrocarbon chains, we categorize them. Saturated hydrocarbons, the ones with only single bonds, are called alkanes. Think of methane, ethane, propane. Unsaturated hydrocarbons with one or more double bonds are called alkenes, like ethene. And the ones with triple bonds, we call them alkynes, like ethine. A good way to remember it, alkanes are full and stable, while alkenes and alkynes are looking for some chemical action.
And it gets better. Carbon doesn't just use straight lines or branched roads. It can literally loop back on itself to create closed structural rings. For example, cyclohexane is a saturated ring made of 6 carbon atoms, all single-bonded. Then you have benzene, C6H6, which is an incredibly famous unsaturated ring that features alternating double bonds. Straight, branched, or rings, carbon can build it all.
All right, section 4, the homologous series. So if carbon builds millions of different chains and rings, how on earth do chemists make sense of them all without losing their minds? We group them into highly organized, predictable families called the homologous series.
Check out this beautiful mathematical pattern. We have methane, ethane, propane, and butane. What is the difference between them? Well, every time you step down the family tree to the next member, you simply add exactly 1 carbon and 2 hydrogens, a CH2 unit. And since carbon has an atomic mass of 12 and hydrogen is 1, every step adds exactly 14 atomic mass units. This creates a perfect, predictable sequence where the physical properties smoothly graduate, but the chemical properties stay really similar.
But what if we want to change things up? Enter the rule breakers, functional groups. If you take a standard hydrocarbon chain and just swap out a single hydrogen atom for a heteroatom like chlorine, or maybe an oxygen-based group like an alcohol or a carboxylic acid, that functional group completely hijacks the chemical properties of the chain. It dictates exactly how the compound will react, and it honestly doesn't even matter how long the carbon chain itself is. Finally, Section 5, Reactions and the Real World. We've built the molecules, we've given them functional groups, we've organized them. Now for the fun part. What happens when we actually make them react? Let's look at the 4 critical reactions that drive organic chemistry.
These 4 reactions are the absolute engine of our daily lives. Number 1 is combustion. When carbon compounds burn an oxygen, they release a massive amount of heat and light. Your textbook points out that saturated hydrocarbons give a nice clean flame, while unsaturated ones give a yellow, sooty flame. Number 2 is oxidation, where we use oxidizing agents to add oxygen to a compound. Number 3 is addition. This is where unsaturated chains pop their double bonds open to add hydrogen, usually with a nickel or palladium catalyst. This is literally how factories turn liquid vegetable oils into solid saturated fats. And finally, number 4 is substitution, where in the presence of sunlight, an element like chlorine can come in and replace hydrogen atoms one by one.
Let's zoom in on oxidation for a second, because this is a classic textbook example you absolutely need to know. Take this equation. When you take ethanol, which is an alcohol, and you treat it with an oxidizing agent like alkaline potassium permanganate and heat it up, the agent literally forces oxygen into the molecule. The alcohol completely transforms into ethanic acid. The starting material gained oxygen, which is the very definition of an oxidation reaction. And all this chemistry is literally sitting in your house right now. Ethanol is a phenomenal solvent used in medicines and tinctures. Ethanoic acid, when you dilute it in water, that's just the vinegar you use in your kitchen. And what about cleaning up? That is the absolute magic of soaps. Soap molecules have a total dual personality. They have a hydrophobic head that loves water and a long hydrocarbon hydrophobic tail that hates water but loves oil. So when you wash your hands, these tails trap the oily dirt in a tiny spherical structure called a micelle, while the heads stay pointed out into the water. You rinse, and the micelle washes the dirt right down the drain. Wow, we have covered a massive amount of ground today, from the energetic dilemmas of a tiny atom to the superpowers of catenation and tetravalency, all the way through to the chemical reactions that clean our clothes and flavor our food. So, I have a challenge for you right now, directly from your textbook exercises. Grab a piece of paper and try to draw the formula and the electron dot structure for cyclopentane. Remember, it's a saturated ring with 5 carbons. Keep building those concepts, stay curious, and I'll see you in the next explainer.